Quantum computers are supposed to be the most powerful computing devices ever built. They should be solving problems that would take your laptop longer than the age of the universe: drug discovery, climate modeling, breaking encryption, and optimizing global logistics. So why aren't they? The honest answer is one word: decoherence. It's the single biggest reason quantum computers haven't changed the world. It's the reason your qubit breaks down in microseconds. It's the reason we need surface codes, error correction, and refrigerators colder than deep space. It is without exaggeration the central problem of quantum computing, and almost nobody explains what it actually is. Most explanations stop at the environment disturbs the qubit. That's true, but it's like saying a car crash is caused by the road being hard. It's technically correct, completely useless. Today we go deeper. We're going to understand what decoherence physically is, why it happens, and what it does to your qubit mathematically, and what the smartest people on the planet are doing to fight it. No prior knowledge needed. Let's go. Before we can understand how a qubit break, we need to fast picture on what they are. A classical bit is a switch, on or off, 1 or 0. It has one job and it does it perfectly. A qubit is different. A qubit can exist in a superposition, a blend of 0 and 1 at the same time. Mathematically, we write the state as this: alpha and beta are complete numbers, amplitudes, and the sum of the squared magnitudes equal 1. The qubit isn't secretly 0 or 1, it's genuinely both in a precise mathematical combination until you measure it. The power of quantum computing comes from the superposition. When you have many qubits, the number of combinations grow exponentially. 10 qubits can represent 1024 states simultaneously. 50 qubits can represent more states than there are atoms in the observable universe. A quantum algorithm manipulates all of these states at once in parallel in a way classical computers simply cannot. But here's the catch: that superposition, that perfectly balanced quantum state, is extraordinarily fragile, and that moment it falls apart, you lose everything. That falling apart is decoherence. Here's a real definition, not the textbook version, the honest one. Decoherence is not the environment disturbing your qubit, it's the environment becoming entangled with your qubit. That distinction matters enormously. Let me explain it. When two quantum circuits interact, a qubit and a single air molecule, a qubit and a stray photon, a qubit and a vibrating atom in a chip, they don't just bump into each other and separate. They become quantum mechanically linked. Their states become correlated in the way only quantum systems can be correlated. They entangle. When your qubit entangles with the environment, the superposition doesn't disappear. It spreads out and it leaks into the environment. The information that was in your qubit's quantum state, the precise values of alpha and beta, get distributed across an enormous number of environmental degrees of freedom. Billions of particles, each carrying a tiny slice of the information that used to be neatly in your qubit. Once that happens, the information is effectively gone. Not because it was destroyed, the laws of quantum mechanics are reversible, nothing is truly lost, but because it's now scrambled across so many particles that recovering it would require tracking every single one of them simultaneously, which is impossible. From the qubit's perspective, it looks like the superposition collapsed. The qubit went from a clean quantum state to what physicists call a mixed state, the classical probability distribution over 0 and 1, with all the quantum interference effects gone. That loss of interference is what decoherence literally means. Decoherence, the coherence, the ability of quantum states to interfere with each other, is destroyed. And without interference, you lose quantum computing. Quantum algorithms work precisely because the quantum states of different computational paths interfere with each other constructively or destructively, amplifying right answers and canceling wrong ones. Take away interference and your quantum computer is just an expensive classical computer making random choices. Physicists characterize decoherence using two timescales. These are the most important numbers in quantum hardware, with every quantum computing lab in the world obsess over them. So T1 is a relaxation time. T1 measures how long a qubit is in the excited state. The Ket1 state takes to spontaneously decay to the ground Ket0 state. This is energy relaxation. The qubit loses energy to the environment like a ball rolling down the hill. It doesn't stay in Ket1 forever, it decays, and when it does, any information encoded in that energy difference is gone. Think of it this way: if your qubit supposedly holds a Ket1 but T1 is only 100 microseconds, you roughly have 100 microseconds before that Ket1 spontaneously becomes Ket0 on its own. No measurement, no gate, just the environment pulling the qubit downhill. On IBM's latest superconducting qubits, T1 times are currently around 262 microseconds. That sounds long, but consider that a single quantum gate takes roughly 50 nanoseconds to execute. This means you get a few thousand gates before T1 kills your computation. Modern algorithms need millions. T2, the dephasing time. T2 is subtler and in many ways more destructive. T2 measures how long the qubit's phase coherence survives, how long the precise relationship between ket0 and ket1 components of the superposition stay intact. Remember, a qubit state is alpha ket0 plus beta ket1. The amplitudes alpha and beta aren't just magnitudes, they have phases, angles in the complex plane. The quantum interference that makes quantum computing work depend entirely on these phases being precise and stable. T2 dephasing happens when the environment causes random phase kicks to the qubit. Tiny fluctuations in electromagnetic fields, vibrations in the material, charge noise from nearby electrons, each kick slightly randomizes the phase. Eventually, the phase is completely scrambled, and the superposition becomes a useless classical mixture. Critically, T2 is always less than or equal to 2 times T1. Energy relaxation also destroys phase coherence, so T2 is bounded above by 2 T1. In practice, on most hardware, T2 is significantly shorter than 2T1 because there are additional pure dephasing mechanisms beyond just energy relaxation. IBM's current transmom qubits show T2 times around 177 microseconds. Trapped ion systems from IonQ and Quantum fare better, with coherence time stretching into seconds. But their gates are slower, so the trade-off is real. The bottom line, your qubit has 2 timers running the moment it initialized. T1 is counting down to when it forgets its energy state, T2 is counting down to when it forgets its phase. Your entire computation has to finish before either timer hits 0. So what actually caused these timers to run? What's the environment doing? The answer depends on qubit technology, and it's worth understanding the main culprits because they tell you something fundamental about why this problem is so hard. Thermal noise. Everything above 0 is just vibrating. The atoms in a chip, the substrate, the wiring, all of them are jiggling with thermal energy. These vibrations create fluctuating electromagnetic fields that couple to qubits and scramble their states. This is why quantum computers operate at temperatures below 20 millikelvin, colder than interstellar space. At those temperatures, thermal vibrations are almost completely suppressed. Almost. Electromagnetic interference. Stray photons, radio frequency noise, fluctuating magnetic fields from nearby electronics, all of these can interact with qubits and cause phase kicks. Quantum computing labs are heavily shielded, but perfect shielding is impossible. Even a single stray photon at the right frequency can destroy a qubit's coherence. Charge noise. In superconducting qubit systems, the qubit is sensitive to the precise charge configuration of nearby materials. Even at millikelvin temperatures, charges randomly hop between defects in the substrate, a phenomenon called two-level system noise or TLS noise. Each hop creates a tiny electric field fluctuation that kicks the qubit's phase. This is one of the dominant T2 mechanisms in superconducting qubits, and one of the hardest to eliminate because it comes from an atomic scale defects in the materials themselves. Crosstalk. In multi-qubit processor, qubits are physically close together. When you apply a gate to one qubit, neighboring qubits feel a residual effect. This is crosstalk, and it causes errors that look like decoherence even when the environment isn't directly involved. Cosmic rays. This one sounds like science fiction because it's real. High energy particles from space occasionally pass through quantum processors and deposit energy into the chip, causing correlated errors across many qubits simultaneously. Google has published research on this. It's a genuine engineering problem. The unifying theme across all of these is coupling. Decoherence happens when the qubit's quantum state couples to any degree of freedom outside the qubit, and the universe contains an incomprehensibly large number of external degrees of freedom. Fighting decoherence is fundamentally the problem of isolating a quantum system from literally everything while still being able to control and measure it. That's a deeply paradoxical requirement. You need to interact with the qubits to run gates, but every interaction is a potential source of decoherence. The entire engineering challenge of quantum computing is threading this needle. So let's make this concrete. What does decoherence actually do to the quantum state? Mathematically, a pure quantum state, a qubit in superposition, is described by a state vector, but once decoherence starts, we can no longer describe the qubit with a single state vector. We need a more powerful object called a density matrix. So the density matrix for a pure state is ket phi, which is seen here. The diagonal entries alpha squared and beta squared are the probabilities of measuring 0 and 1. The off-diagonal entries are the coherences. They encode the quantum interference between 0 and 1 components. These are the entries that make quantum computing work. Now watch what decoherence does. As the qubit interacts with the environment, the off-diagonal entries decay exponentially. The coherences shrink towards 0, and after a few T2 times, the density matrix looks like this. This is diagonal density matrix, a classical probability distribution. No coherences, no interference, no quantum computing, just a coin that lands heads with a probability and tails with another probability. The quantum information didn't disappear in a physical sense. It's still out there, encoded in the correlations between the qubits and the millions of environments of particles entangled with. But from the qubit's perspective, it's gone, irreversibly scrambled. This process, off-diagonal elements decaying to zero, is what physicists mean when they say a quantum state decoheres into a classical mixture. So let's connect this to why quantum algorithms fail. Quantum algorithms work through interference. The canonical example is Shor's algorithm for factoring large numbers. It encodes the factoring problem into a quantum superposition of all possible factor guesses simultaneously. Then through the sequence of carefully designed quantum gates, it engineers the interference so that wrong answers cancel out and the right answer is amplified. This interference is entirely dependent on the coherences, those off-diagonal elements in the density matrix, surviving intact through the computation. If decoherence kills those coherences partway through, the interference breaks down. Wrong answers stop canceling, right answers stop amplifying, the algorithm produces garbage. This is a circuit depth problem. Every additional gate you add to the quantum circuit is an additional time during which decoherence is eroding your coherences. The depth of the circuit, how many gate layers it contains, must fit within the coherence time or the computation fails. Current superconducting hardware can execute roughly a few thousand gates before decoherence makes results unreliable. Shor's algorithm for a cryptographically relevant problem needs millions of gates. QAOA for real optimization problems need hundreds of iterations for many qubit circuits. Quantum chemistry simulations for drug discovery need circuit depths that are orders of magnitude beyond what current hardware can sustain. This is a gap between quantum computers today and quantum computers that will actually change the world, and decoherence is a wall standing between them. The good news is that the physics of decoherence is well understood, and researchers have developed several strategies for fighting it. None of them are complete solutions yet, but together they're making real progress. Better hardware. The most direct approach is simply building qubits with longer T1 and T2 times. Superconducting qubit coherence times have improved by roughly a factor of 10 every 3 years since 2000. In 2010, T1 was a few microseconds. Today, it's hundreds of microseconds. IBM's roadmap targets millisecond coherence times within a few years. Trapped ion qubits already achieve coherence times of seconds. Photonic qubits are naturally resistant to many forms of decoherence. Every hardware platform is in a race to push T1 and T2 as high as possible. Better isolation. Dilution refrigerators, electromagnetic shielding, vibration isolation, materials engineering to reduce charge noise. Google's latest chips use substrate improvements specifically targeting TLS defects. Microsoft is pursuing topological qubits, a fundamentally different qubit design where the quantum information is stored in a non-local way that makes it inherently harder for local decoherence to destroy it. Dynamical decoupling. This is an elegant technique where you apply carefully timed sequences of controlled pulses to the qubit during idle periods. The pulses effectively average out the environmental noise. The phase kicks in from the environment partially cancel each other when the pulses are timed correctly. This can extend to effective T2 by an order of magnitude without any changes to the hardware itself. It's essentially using the qubit's own controls to fight its own decoherence. Quantum error correction. This is the big one. The approach that, if it works at scale, solves decoherence permanently. Rather than trying to prevent decoherence, quantum error correction encodes logical qubits across many physical qubits in a way that allows errors to be detected and corrected continuously. The surface code, which we covered in a previous video, is the leading approach. In 2024 and 2025, Google, IBM, and Quantum and QEra all demonstrated logical qubits that are actually outperformed by their physical qubits, meaning error correction was working better than the raw hardware. This is a threshold crossing. It proves the approach works. The catch is overhead. Current surface code implementations need roughly 1,000 physical qubits to protect one logical qubit at the error rates achievable today. A million physical qubit machine, which nobody has yet, could run algorithms on about 1,000 logical qubits. That's not enough for most practically useful computations. Getting the overhead down is the central engineering problem of the next decade. So let's zoom out and place decoherence in the full context of quantum computing. Decoherence is not a bug. It's a fundamental feature of quantum mechanics. The same quantum entanglement that gives quantum computers their power is also what connects qubits to their environments and causes decoherence. You cannot have one without risking the other. This is why quantum computing is hard in a way that classical computing never was. Classical bits are robust. A transistor holding a 1 either holds it or it doesn't, and if it doesn't, you notice it immediately and fix it. A qubit losing coherence is invisible, gradual, and affects the entire quantum state in a way you cannot directly observe without destroying the computation. The entire field of quantum error correction exists for one reason: to make quantum information as robust as classical information without destroying what makes it quantum. And the remarkable theoretical result proven by Shor, Steen, and Kelderbank and others is that it's possible in principle. There is a threshold error rate below which quantum error correction can suppress errors faster than they can accumulate. Cross that threshold and you build arbitrarily reliable logical qubits from imperfect physical ones. We are currently in the process of crossing that threshold in practice, not just in theory, and results from 2024 and 2025 show it working at a small scale. The challenge now is scale scale, more physical qubits, lower error rates, and faster classical decoding to keep up with the syndrome extraction happening millions of times per second. Decoherence is a dragon. Quantum error correction is a weapon. The question is whether we can build the weapon fast enough and scale it up far enough. The answer, based on where the field is right now, is almost certainly yes. The only question is when. Every major quantum computing milestone you will hear about in the next decade, every announcement from Google, IBM, Microsoft Quantum, IonQ, will ultimately be about one thing: coherence time, error rates, logical qubits. All of it comes back to the war against decoherence. Now you understand what the war actually is. Thanks for watching, keep questioning the quantum world, and I'll catch you next time.